So you are welcome. Our discussion today is on lenses. So we are looking at the type of lenses we have, how the images are formed when an object is placed in front of lenses. So let's look at it. So a lens is a curved block of glass or plastic that allows the transmission of light through it. So they are made of glass or plastic and they allow the transmission of light through it. So there are two types of lenses, which are the convex lens and the concave lens. So a convex lens is thicker at the middle than it is at the edge. So if you look at the convex lens, the middle is very thick and the edges are thin. So if parallel light rays are passing through the convex lens, these rays are brought to focus at a point. They are brought to be focused at a point. So we can therefore term the convex lens as converging lens. So the convex lens are also termed as the converging lens. So if you look at this diagram, rays entering the converging lens refract inwards. Rays entering the converging lens refract inwards as it enters the lens and inwards as it leaves the lens. So if you look at this ray coming into the lens, it's refracted inwards, and when it is leaving also, it refracts inwards. So the rays coming into the lens, when they are parallel, they are brought to a focus. So for convex lenses, a parallel light ray parallel to the principal axis passes through the focus on the other side. A parallel light ray parallel to the axis passes through the focus on the other side. So if you look at the rays here, and we consider this to be the principal axis passing through the optical center of the lens, these rays, which are parallel to the principal axis, refracted through the lens and they are passed through the focal point. So these rays pass through the focal point since they are parallel to the principal axis. And the ray through the optical center goes straight without deviation. So if you look at this ray, passing through the optical center, it moves straight in through the lens without refraction. So it is transmitted through the lens and goes straight to the focal point. And a ray through the focus emerges parallel to the principal axis. A ray through the focus emerges parallel to the principal axis. So if a ray is coming out of the focal point into the lens, this ray therefore travel parallel to the principal axis. So it is similar to the first, but it is a vice versa of it. So convex lenses are used for manufacturing glasses. They are used for manufacturing magnifying glasses. So magnifying glasses has convex lenses in them, and the cameras we use, convex lenses are used. Hyperbia correction and microscopes, they all use convex lenses. So a concave lens is thinner at the center and thicker at the edges. So it is the opposite of the convex lenses. So with the concave lens, the inner is thin and the edges are thicker. So parallel light rays are diverged as they are coming in from a virtual focus. So if the parallel light rays are coming and they enter the diverging lens or they enter a concave lens, these light rays, they are diverged as they enter the lens. So they are also termed as diverging lens. So concave lens are also termed as diverging lens. So if you look at this diagram, the light rays are parallel and they are moving onto the diverging lens. So as they enter the diverging lens, the light rays diverge. And the virtual rays are drawn to a focus. So for concave lenses, which are also termed as diverging lens, a ray parallel to the principal axis appears to diverge from the focus on the same side. It appears to diverge from the focus on the same side. And a ray directed toward the focus emerges parallel to the principal axis. It emerges parallel to the principal axis. And the ray through the optical center goes straight without deviation. The rays through the optical center goes straight without deviation. So concave lenses are used for myopia correction, laser beam expanders, peepholes, and etc. So these are the uses of concave lenses. So when we take the focal length of lenses, It is the same for light rays passing through the lens in inner direction. If you look at this diagram, the focal length on the right side is same as the focal length on the left side. So the focal length are the same on both sides of the lens. The focal length characterizes the lens, hence it's a property of the lens. So every lens has its specific or unique focal length. Every lens has its specific focal length. So now we are looking at object and its image location from convex lens. Object and its location from convex lenses. The first one is when the object is at infinity, the image is formed at the focal point and its size is reduced to almost like a point. So if you look at this diagram, the object is at infinity, therefore the rays coming are parallel to the principal axis. So when they enter the convex lens, the image formed is at the focal point and it resembles a point. So the image is like a point at the focal point. The image is like a point at the focal point. And the second one is when the object is placed at C, which is the object distance is greater than twice the focal point. The image is formed between F and 2F. So if you look at this diagram, the object is placed at a distance greater than 2F. It's placed at a distance greater than 2F. So the object distance greater than 2F, therefore its image is formed between F and 2F. The image formed between F and 2F. And also when the object is placed at twice the focal point, the image formed is at 2F. So the object at 2F, the image will also be at 2F. So the diagram here depicts the explanation. The image is at 2F and the object is also at 2F and they have the same size as the object. The image has the same size as the object. The fourth one is when the object is placed between F and 2F, the image is formed beyond 2F on the other side of the lens. The image is formed beyond 2F on the other side of the lens. So when the object is between F and 2F, the image is formed far behind 2F on the other side. And the size of the image becomes greater than that of the object. And now, when the object is placed at the focal point F, the refracted rays are parallel, hence no image is formed. If you place the object at F here, the image is formed at infinity. The image is formed at infinity, or we therefore say that the rays that are refracted through the lens are parallel. They do not meet, so no image is formed at all. And the last for convex lenses are when the object is placed between the focal point and the optical center. That is, the object distance is less than the focal length. The image formed is virtual and it is formed between F and 2F at the same side where the object is. So if you look at the diagram here, the object is placed between F and O, which means the object distance is less than the focal point. So the image formed is virtual. It is formed on the same side as the object, and its size is bigger than the object. And the image is also formed between F and 2F on the same side of the object. So these are how images are formed when an object is placed between convex lens. Now let's look at how images are formed in their location when an object is placed in front of a concave lens. So when the object is at infinity, the image is formed at the focal point with a point size. The image is then virtual, erect, and smaller than the object. So if you look at the diagram, when the image is at infinity, the rays coming are parallel to the principal axis, and therefore the image formed is at the focal point and it has a point size. And it is virtual. Since the diverging rays are drawn to focus at F. And the second one is when the object is placed at a finite distance from the lens, a virtual image is formed between the optical center and the focal point, and the image is smaller than the object. So we have the object placed at a finite distance, let's see, between F and 2F of the lens. The image then formed is between F and the optical center O. And the size of the image is smaller than that of the object. And it is a virtual image as well, since the diverging rays are then drawn to meet to form the image.